First, I would like to thank this invitation to me that to give a mini course on local theta correspondence. So I will just basically, at least for the first today's talk, I will just follow Gan-Kudla and Takada's notes. So it is a very long notes. I can show you that it has 632 pages. But don't be scared of this note. So today we will cover 150 pages. Okay, so this is a very detailed account of the definition. I think it's the best account of the definition of wave representation. It contains all the details, and every small bit you certainly will be confused by. And certainly I was not 100% sure when before I prepared this talk. So it explains. So it has, I think, enough detail for you to like follow if you really want to know the detail, really want to know the, right. So how to compute something. But on the other hand, because you see that local long length, local theta correspondence has been studied by so many people, and like me, I have studied the local theta correspondence for quite a while, more than 10 years, but I still don't understand the many technical details in this. It means in the most of the case, you can ignore the technical detail. Okay. But if you really want to compute something, you need to know these formulas. Okay. I think maybe I should. Right. Maybe later I will sit, but now let me stand. So this is my plan. So probably I will give 5 lectures. Each will be 1.5 hours. So the first one will be the wave representation, how to define it. So it's a big achievement by the Weil and the Rao and a lot of peoples. So although it's a basic of the whole theory, but itself is not basic topic. Okay, then I will talk about theta correspondence over finite field. So this topic is like, I think 5 or 6 years ago, it's still like it's a myth, but nowadays all the correspondence, at least the representation theoretical level is known. So you can explicitly write down the correspondence for the theta over finite field. And so the third talk, I will cover some basic stuff for theta over real numbers. And the fourth, I will cover some basic stuff. Actually, it's some stuff what I understand for the p-adic case, because you actually have a lot of different approach to the p-adic theta correspondence. Okay, then the fifth one, I will talk about the geometry involved in the theta correspondence and maybe some relations with Gan-Kudla-Takada. Okay, so let's move on to the first part. So we are going to define what is a wave representation. So the setting is that we will take a field whose characteristic is not equal to 2. And so if the characteristic is equal to 2, then okay, there's no agreeable among experts how to define for the wave representation. Okay, so notice that this condition does not mean that the residual characteristic cannot be equal to 2. So if for the p-adic group, you can like define the wave representation for Spn over Q2. This can be defined, but Q2 it still has characteristic 0. Okay, so we will so the very beginning we will take a non-degenerate symplectic space W, which means that you will have a pairing like this, so that Okay, so you have a symplectic pairing such that the bracket x y is equal to bracket minus a minus bracket yx. Okay. Right. And so from this, we will define the Heisenberg group in the way that as a set, it is just a product of W and the field. And the multiplication is defined by W by this formula. So the point is that you will have this extra term, okay, which given by the symplectic form. And you have a half here, so which requires that 2 is invertible in this field. Okay. Of course, you can erase half, but then somewhere 2 will appear in the formula. Okay, so the useful formulas include that you can very easy to compute the inverse of this element. WT inverse is just minus W minus T. This is because the pairing of W with itself is 0. Okay, so you also have this formula. If you have 0 W plus W prime, then you can write it as multiplication of W and W prime, but you have a discrepancy, which is half and W prime. Okay, so the point is that you can see the center of this group is actually given by T, by this F. So the center is just this F. The center is just this one. Okay, so this consists of element 0 T where T in F, so it's isomorphic to F. So there will be a theorem I'm not going to prove, but I just quote it is okay. Wait. It is Stone-von Neumann theorem. It says that for any non-trivial additive character, additive character means that psi A plus B is equal to psi A times psi B. Okay. So there will be a unique irreducible smooth representation rho psi. So of course up to isomorphism such that the center is acted precisely by the center is precisely acted by the scalar phi t. Okay, so this is the multiplication by the scalar phi t. So we will call this isomorphism class the Heisenberg representation of this Heisenberg group. So the name coming from Heisenberg is because so usually you will have a polarization like W is equal to X plus, okay, so Y, and the X is a totally isotropic space inside W, and the Y is also a totally isotropic space inside W, and their intersection is 0, then this X and the Y will be called the Lagrangians. So these are maximal possible dimension totally isotropic subspace. Okay, what does it mean? Do I need to explain what is a totally isotropic means? So a subspace inside a formed space of, for example, this symplectic space is called totally isotropic if for any vector inside the space, the pairing between these two vectors is 0. Okay, so this is called totally isotropic. So why this is called Heisenberg is because Heisenberg is a physicist. So he studied the canonical commutator relation between the operator of taking momentum and the taking position. So X usually is a coordinate system, so it's taking position of a particle. and the Y will be the dual of X, which is taking momentum. These two operator, like, will have canonical commutative relation. And so he formulates it in terms of matrices. So then you will see this kind of Heisenberg group as a matrix group in the form that it looks like this. One, and this is a vector X, this is a vector Y, and this is a vector T. And this is 0. So it's a 0, 0, 0, 1, something like this. This is X. This is Y. Okay, so you have block diagonal block matrices look like this, and so it's a Heisenberg. Okay, so it's really related to quantum physics, and why it's called Stone von Neumann is because okay, so at the very beginning of quantum mechanics, Schrödinger has defined write down the Schrödinger equation and define the quantum mechanics. And von Neumann, so Heisenberg used the matrix to define the quantum mechanics. It's apparently not clear whether these two quantum mechanics are the same. So then von Neumann, Stone von Neumann proved that they are the same, because this is the only representation you can have such that the scalar is this side. Okay, so it means that the world have different models, like you have Schrödinger model and you have this matrix algebra models called that. Right. So so therefore of course Heisenberg's model is over real, so therefore it's actually Heisenberg's model is corresponding to the so-called Fock model in the real case. But I would like to say that you actually have different models, different way to write down, realize the Heisenberg representation. And it is a very important observation. So we will spend quite a lot of time now to study how to get the Heisenberg representation. So all the models actually coming from one construction. So the construction is in this way. Suppose let's take A, which is a subgroup of W, additive subgroup. So W is itself a vector space, so it's an additive group. So you take arbitrary additive subgroup A inside W, and we define A perpendicular to be the space set of elements in W such that the pairing of A and the W evaluate at psi is equal to 1 for all little a. Okay. So this is A perpendicular. So the typical case is that, like, if X and the Y are totally isotropic, they are Lagrangian, then X perpendicular is equal to X in this case. Okay, so this implies that. Okay, so right, I think I've said that. So you have that X perpendicular equal to X. Okay, so this condition is called a self-dual. If A is equal to A perpendicular, it will be called a self-dual. So I have give you an example of self-dual is that if you have a polarization, which means that decompose the symplectic space into direct sum of two Lagrangians or two totally isotropic space, then each space itself is self-dual. So in this case, X is half dimension of W, and the Y is also half dimension of W. Okay, so this is called a so it's suppose you have a subgroup which is self-dual, then you can, yes.
So from the definition, If the total as profit will be lies inside the curve, what does equal curve? So it's independent of time.
Because you have the polarization, X and Y are Lagrangians, they are maximal totally isotropic.
But you also have a factor.
What?
You also have the factor to define it.
Which one?
A curve. The definition A curve, you have a factor.
Yeah, you need a character.
Yeah. So what you mean is this, if the total as profit is independent of time.
This is because for any thing in X, you can find Y here. Okay, so this is because for any Y non-zero, you can find the X such that X paired with Y is equal to arbitrary element in F. You take arbitrary element in F. So therefore, so this psi is assumed to be non-trivial, so it must be non-zero at certain point. Okay. Right, very good point. So there's another case. There is another case that you will have a self-dual subgroup, which is A is a lattice inside W. So suppose, okay, let me just go to for lattice model. Okay. Lattice model is in this defined in this way. So suppose let's somehow choose the character psi to be like have a conductor R. So for simplicity, you can assume the conductor is just R is just zero. So which means that R is so in the p-adic case anyway. So in the p-adic case, you have a ring of integer. I will denote it by O. Then you will have a smallest number called the conductor of the character such that psi restrict on the pi R times O is equal to trivial. So this minimal number is called conductor of psi. Then if you have a lattice, so you can see the perpendicular will also be a lattice. Okay, so we can somehow define self-dual lattice. Which means that this lattice is equal to its perpendicular. So in this case, you always can find a basis, more or less a symplectic basis, En to Fn, such that the pairing between Eij and Fij is equal to 0, and the pairing of Eifj is equal to delta pi r. Okay, so this is the case, another case of self-dual subgroup. Okay, so you also can interpolate between these two cases. Like certain part you take lattice and a certain part you take isotropic space, but then this will give you mixed model. But anyway, so the point is that as far as, okay, so the construction works for all the fields. Okay, as far as you include the local, finite, and the real. But anyway, as far as you have this self-dual group, then you can define HA, where HA is just the subset A cross F in HW. So it turns out because the self-dual requirement, this is actually a subgroup inside the HW. And then we have a character on F here. We have a character on F here, so which is a psi. Okay, so somehow we have to extend. We can, okay, so the point is that there exists an extension. Of course, the extension is not unique, such that psi, so such that its restriction on F is this psi. Okay, you can choose arbitrary extension and do the induced representation, which means that it is smooth function on HW. So it's quite technical to define what's the meaning of smooth for p-adic group. So roughly speaking, it means that for any function, it is fixed by an open compact subgroup under the translation action. Okay, right translation action of this function. So this is called smooth. So you just take a smooth function from the group to C such that it satisfies this equivariant condition. This is that FKH is equal to psi AK FH. So you take the set collection of all these functions. So it will have action of HW by left translation. By right translation, sorry. So it's act by right translation of these functions. So this is the so-called induced model. All the other models coming from this model. So there are some remarks. The first one is that the isomorphism class of this row A is independent of choice of phi A. So this is a simple McKay theory argument. So we will skip it. So actually, I will not give any proof today. So therefore, we just use psi A. We ignore the row A. We ignore the psi A. And another thing is that so for any element, you actually have an open subgroup such that it is fixed by this open subgroup under the left translation. And this condition will actually tells you that the support of F is contained in the HA translation of some kind of U perpendicular, where U is a subgroup inside the W. Okay. So anyway, so this point is that the support of F is at least in the p-adic case, the support of F is compact mod HA. So this means that the support of F is compact. Okay. So therefore, you can also view this model as a compact induction. Okay. So maybe you don't see the point at current stage, but later you will see why we need the compactness. Okay, so actually next line you will see the compactness. Yes, this is because we somehow want to do integration. So we want to make sure the integration converge. So that it will have a natural, so this representation will have a natural unitary structure given by integration along the quotient space of HW by HA. So this is roughly speaking just you have a cross section. This is just A quotient or A quotient W. All right. Wait. Okay, you know what I mean A quotient. Anyway, so the point is that you can have a unitary structure, as we know that the quantum mechanics is built on the unitary structure. Okay, so this is for p-adic case. What about the real case? Real case is the same. So somehow you will take smooth functions satisfy this condition, and you require that the function is like rapid decay, maybe if you want to study a smooth model, or if you want to study unitary representation, you require this integration converge. You just pick all the functions such that this converge. So this will be the L2 model of the wave representation. Okay, so the last one is that for all different choices of A, rho A will be model of Heisenberg representation of X star. Okay, so let's look at so pretending we are Schrodinger. So we write down the Schrodinger model of the quantum mechanics, which so in the setting that W is equal to X plus Y, where X and Y are totally isotropic. So this will imply that X is self-view. So we will take the extension. So under this polarization, we will have a unique extension of this psi by you just send xt to psi of xt. Okay, so this is the most naive extension of the psi on F2. Okay, so HX. Okay, so right, we will certainly have this induced representation, but this induced representation is not that concrete. So first of all, it is all the element in this induced representation lives on the group Heisenberg group. It has so if X has dimension n, then this will have 2n plus 1 dimension. So we want to reduce the dimension. So actually, you will have a natural embedding of Y, right? To the Heisenberg group HW. Okay, so you can pull back function on HW to Y. So this is a restriction. So the point is that the restriction from F to so the function on the group to the Y will give you an isomorphism of vector space. And then if you have a group representation of the Heisenberg group on the left-hand side, then by translate the structure, you will have a representation on the C infinity Y. Okay, so why the image is in CC infinity Y? So this is the place compare induction appears. So we said that the function f is actually has compare support mod X A. Okay, so therefore the image restriction is actually a completely supported function on Y and locally constant, which means that for any point, it will have an open neighborhood of this point such that the function is constant on this open neighborhood for the p-adic case. Okay, for the real case, so if you take the smooth model, this side will be the Schwarz function on Y. If you take the L2 model, this will be L2 function on Y. Notice in the real case, Y is just a n-dimensional vector space over real Rn just. So you will have L2 function on Rn. Smooth model, you will have Schwarz function on Rn, which is smooth and rapid decay. Okay, so you just unwind the definition, you can see that the action of a Heisenberg group element. So every element can be written as X plus Y, where little x is in capital X, little y is in capital Y, and the T is in F, such that the action of any function psi, any function phi, take value at y0 is given by this formula. Okay, so it looks scary, but it's okay that you just put x is equal to 0, then you see that y is just x by translation action. When x is equal to 0, this, okay, little x is 0. So this term will go to 1, right? So this is just the sigma y is just phi is just the translation.
Sorry, Prof. What is your phi again?
So phi is the element in the in here. Sorry, I should write it. Phi is so phi is inside here.
Okay, thanks.
Okay. So it's just a function on y. So then this is just phi y0 plus y. And so the another case is that when y is 0, x is non-zero. Then in this case, it's just a multiplication. So you see that it's just a multiplication of the let me try to type maybe even faster. So sigma y xt is just a psi y0 x phi y0. Okay, so okay, so you see that it's just a multiply, more or less multiply the non-trivial character on the element. Okay, so if you do the Fourier transform, then you will see that it will again be the translation as the Fourier side. Okay, so later we will mention this. So as a consequence, so this model will be called the Schrödinger model of the Heisenberg representation, and it's actually depends not only on y but also on the polarization. So also depends on x. So but anyway, you can see that there's some interesting fact is that if you switch the role of x and y, then the resulting representation are essentially the same, but up to a contragradient, or maybe, so actually the contragradient of rho psi y is isomorphic to rho x, but with the character taking the conjugation, or maybe contragradient of the additive character of the field. Okay, so this is one model. Another model is called the lattice model. So I think I've mentioned this before, that you take a lattice inside W. Lattice means that it is a free O module inside W such that tensor with F will be the whole W. Okay, so then you can define the perpendicular is just given by this. And okay, you can calculate the perpendicular is actually the or element in W such that WL pairing is contained in pi R O, where I is the conductor of the character. Okay, as a consequence is that this perpendicular is also a lattice, and some linear algebra will tell you that a lattice is self-dual if and only if you can find a basis satisfy this condition. Okay, so so it comes a little bit additional complexity is that if you want to deal with problem when the field has characteristic 0, but residual characteristic 2, then you have to further take a polarization using this basis of the lattice so that you extend the, so we always need to extend the psi to HL. Okay, so the extension is given by this formula. Okay, so the extra complexity is because you wish the formula also works for residual characteristic too, so you will have this formula here. So if so I think if the residual characteristic is not equal to 2, you can take the naive extension. You just let it be trivial on L. Otherwise, this one will not be inside the pi R O for arbitrary element L. Okay, then it's a non-trivial extension of the to L, non-naive extension. Okay. So this is a comment that if the characteristic of the residual field is not equal to 2, then this L psi L is just LT is just a psi T. Okay, so I think in the most of the case you can ignore the P equal to 2 case. Okay, so the lattice model yes.
You said that L is something we can only find such a basis.
Yes.
What is this choice of basis?
It's not unique.
It's not really.
Oh, sorry. L is spanned by E and to E.
So L is spanned by
Yeah.
E1 to En or
Yeah, E1 to EM and F1, Fn. As a lattice over, as a free module of O. Okay. Yes.
As the all the models they are Heisenberg.
Yes.
Finding takes
Yes.
So also if that rho A, the index module is independent of A.
As the representation, the isomorphism class is independent of A. But they are physically different representations. They realize on different spaces. All these spaces are subspace of functions on HW. So this is different collections of functions on HW. Yeah, this is a very good point that later we will change the model. Okay, so again, some simple calculation will tell you that okay, the basic observation that W is of course naturally surjective to HL divided by HW. Okay, under the natural map. And therefore, it means that the restriction of the function of W's will give you some functions on W, but it turns out that these functions will be completely supported and satisfy this kind of this equivalent relation. Okay, so this formula, so this side, CC infinity W psi L will be called the lattice model attached to the self-lattice L. Okay. A priori, it's just a function on W. So, but it is completely supported and it transform according to this one. So from this one, because it's completely supported, actually you can see that this is a locally constant function also. Locally constant, completely supported function on W satisfy this condition. Okay, so this is another concrete model of the wave representation. So the point is that this is isomorphism. Okay, so you have induced model, so you have group action on the induced model, transfer the structure, you will get the group action on this space of the Heisenberg group. And then it turns out you can work out the action. So you don't have, so in this case, you will have the action given by this formula. It looks cleaner than the Schrodinger model, right? But you have the you have to trade off. You have some trade-off. The trade-off is that, so in this model, functions is on a 2n dimensional vector space. In the Schrodinger model, your function is on an n dimensional vector space. And okay, so you also can see this from the non-trivial definition, or like involve the definition of a CC infinity W psi L. You see that it's not arbitrary compact support smooth function, but it should satisfy certain equivariant condition. But if you compare the Schrodinger model, you see the right-hand side is just arbitrary functions compactly supporting smooth. Okay, so I would like to say that in certain case, it's still the translation. When it is still the translation is that when your function is supported on large has a certain support, as far as inside this half W prime W is contained in large enough power of prime power then of F, then this will be just a trivial action. So then this W action will still be like a translation action. So for this reason, lattice model is good for study the compact subgroup action on this Weil representation. Okay. For example, if you want to compute the GK dimension of the Weil representation, you can use lattice model. Okay. So, right. It's interesting to do it. One of the interesting things to do is change of model. So if A and B are two self-due subgroup of W, then okay, so this is why Gan-Kudla-Takada spent so large amount of text to just define the Weil representation. So they are very detailed. That it will tell you that because you have you are allowing arbitrary extensions of the character psi to this HA and HB. So for this situation, you will have an element called a W such that it specifies this formula. Okay. Anyway, this is a technical condition. You can totally ignore it. Just admit that in the most of applications, this W is just 0. Okay. So actually, in all the literature, this W is 0. I think. Okay. So then you will have a change model map. So such that send the induced representation to induce another model of induced representation. So what you do is, you see this is a function on HW. This is a function also on HW. So the naive way is you just map F to F, right? However, if you map F to F, it does not satisfy the equivariant condition imposed on the induced representation. So what you do is you just average against the character on HB, so that make it satisfy the equivariant condition. So if you unwind the definition, then you can see that this. So do some change of variable, you will see that it can be represented by this integration. It's just the manually enforced that f will map to a function such that satisfy the equivariant condition. And then because this has unitary structure and here also has a unitary structure, you can like change the measure here so that makes this map preserve the inner product so that it becomes a intertwining a map between unitary space and preserve the inner product. And the fact is that so in this integration it depends on W, but remember W is always 0 in most of the case, in all the cases, I think I know. So that in fact so the inverse of this intertwining operator is just the IBA. When W is, okay, in general, it's a minus W, but W is 0, minus 0 is equal to 0. So therefore, the inverse of the operation is this one. And so you can do the change of model. For example, you can change X to Y, Y to X. Then we have the RXY, which is from the Schrodinger, from the induced model to the Schrodinger model. And then this intertwining operator will be translated by the this RXY to the very familiar Fourier transform. Right. So this is the Schrodinger. So the first place you have encountered the Fourier transform in the study of Weil representation. I think the importance of Weil representation is because it contains the Fourier transform. Okay, so there's some other stuff I will not cover today, but maybe cover later, is that you actually can have a mixed model and a generalized lattice model. So the idea is very simple. So recall that a priori we want our group A, subgroup of W, this A is self-due, which means that A perpendicular equal to A. But you can relax this condition. You just find any subgroup B such that B contains its perpendicular. So in this case, you will have a self-due lattice, a self-due subgroup such that the B perpendicular is contained in A perpendicular, and the A perpendicular is equal to A, and A is contained in B. Then you can have, you still make this induced model, but however, you can have induction by stage, so that you can have induced. So you have a tower of group HW contain HB and contain HA. Okay, you have a tower of group like this. So you first induce to HB, then you induce from HB to HW. Okay, so this induced representation somehow can be realized as the Heisenberg representation of smaller group. So if it's a lattice, then it will be a Heisenberg representation of the finite field, a generalized lattice model. Otherwise, it will be like some kind of other Schrodinger models of smaller symplectic space. And then you do the induction of stage by stage, so you will see the mixed model. So yeah, so I will make it more explicit later. There's some kind of additional properties of Weil representation is that it is functorial. So first of all, what's the relation between the conjugation of the Heisenberg representation? The conjugation of the Heisenberg representation is the Heisenberg representation of the conjugation of the character psi, and it's also equal to the Heisenberg representation attached to the minus of the symplectic form of the original space. So you see that actually HW physically equal to HW minus. So where HW minus is the space that with the same underlying space of W, but the form is minus of the original form. So it has a pairing that XY under the W minus pairing is equal to minus XY under the original pairing. Okay, so from this symplectic form, you also can define a representation of HW. This is because physically these two groups are the same. So if you view them, both are inside the endomorphism of W, this big group. Okay. And there's another functoriality which says that if you have multiplication, the direct sum decomposition as orthogonal symplectic spaces W1 and W2, then you will have also have a map J12 from the Heisenberg group of W1 cross Heisenberg group of W2 to Heisenberg group of W by the W1, T1, W2, T2 map to W1 plus W2 and the T1 plus T2. So why this is a group homomorphism? Because the pairing between W1 and the W2 is always 0. Okay, then the pullback of the Heisenberg representation of HW to HW1 cross HW2 is nothing but the tensor product of the Heisenberg representation of the two smaller Heisenberg groups. Okay, so this is the functoriality. So it will also be very useful later. So actually the construction of the splitting is also quite naive. So you have this induced model. If you change A is self-due, then G times A is also self-due because G preserves the inner product. Okay, so you have a induced model by A, so you will also have an induced model by GA. Then it's a simple calculation that this F is anyway a function on HW. So you just left translate by G. So it will be a function again on W, and you check it satisfies the equilibrium. Okay. So this is the fact. But you see, this is another model of the induced representation. But if we want to have an intertwining operator, we have to get back to this HW, HA, induced from HA to HW, right? So what we do is we do a change of model integration. So recall that in this side we have a change of model integration. Okay, we change the model from GA to A by using this integration. So the naive splitting, and actually this is the most natural splitting, is just you first left translate to this GA model, then use the integration, force it to be on the A model. Okay, so therefore if you write out the formula, it's just this integration. Okay. So you see why the Weil representation is interesting is because it forces you to do a lot of integrations of certain functions. Okay, I forgot to mention that in all these cases you have to properly normalize the measure for the integration, but you have basically only one choice, is to make everything unitary. Right. So our goal is to define the metaplectic group and the Weil representation. So the natural idea is that so this will be more or less a representation related to the symplectic group, but not exactly. So what is a symplectic group of a symplectic space W? This is nothing but a collection of all invertible linear transformations on W such that it preserves the form. And so this SW will introduce automorphism of the Heisenberg group HW. It only acts on the first factor of the Heisenberg group. And so we have, suppose rho phi S is a Heisenberg representation of the Heisenberg group. we assume the representation realized on a complex vector space S, then this representation is nothing but a group homomorphism of HW to GLS. Okay, so because we have an automorphism on HW, so we can pull back this representation by this automorphism G, so it will give you a new representation. But since this G do nothing on the center, so rho G phi is isomorphic to rho phi by Stonewall-Neumann. So this means that up to up to scalar, there will be a unique operator M. So I also call it MG, such that M intertwines rho phi and rho G phi S. Okay, so this we send a map G as we define the map M to be a map from map G to this intertwining operator MG. So this will give you a projective representation of SPW. So the goal is to lift this projective representation to certain group. So the first step is we consider a very large group in many cases. So it's called MPC cross phi S. This is nothing but a subgroup inside the product group SPW cross GLS. Here, this capital S is a realization of the Heisenberg representation, such that G and M, this pair, satisfy the intertwining relation. So it will have a two natural map. One is a projection to the first factor, another is projection to the second factor. So the projection to the second factor is actually the very representation of the MPC cross on the S. Okay, the first factor is to the symplectic space of W, symplectic group of W, and it turns out this gives you a short event sequence showing that MPW C cross is an extension of SPW by C cross. Okay, so this extension is not a direct product. So we want to understand it by choosing a splitting from SPW to MPW. So the natural construction of splitting is using integration operator. So the idea is that you have an induced model of HAs, and this induced model is just a collection of functions on HW. If you left to translate by G inverse, you can check the function will satisfy the condition for induce from HGA to HW. Okay. But we want an intertwining operator, so eventually we want a map. This is goes to induce of HA to HW of some. Okay. So the dashed arrow part, how we resolve it is that luckily in the previous section we have GIGA, this change of model integration. So if you unwind it, you will have this kind of integration formula for the natural choice of the intertwining operator. Okay, so you can check that this MA. So the point is that the G sends to GMAG. Okay, so as far as for the group extension, we know that if you have a splitting, then you can start to define the cocycle associated to this splitting. It is just the difference between MAG1 times MAG2 with MAG1G2. Okay, so this CA psi G1 G2 is a number appearing in C cross. Okay, and recall that this this CA psi is actually satisfy the co-cycle relation like this. So this is a 2 co-cycle. Okay, so we also know that if we have 2 co-cycle which are homologous with each other, then they will actually define 2 isomorphic group extension. Okay, so the rest part of the difficulties of the theory is to compute the co-cycle. So we have to introduce other stuffs. So the point is to compute the co-cycle in the Schrödinger model. So we have induced the model, and we have this restriction so that we go to CC infinity Y. And so this MXG will be translated to RXYG or just the RG. So in this case, the integration as the induced model will become an integration on functions of Y. I think unfortunately this is a typo, this should be Y, and it's also a typo in their book. Okay, anyway, it's just certain integration. We will not explicitly evaluate it now, but there are some properties like Rxy is not equal to Ryx in this case. And you will have this kind of formula, co-cycle formula for the multiplication, but it's not important. This is just the pullback of this co-cycle formula, definition of co-cycle formula of MA. Okay, so the rest part of this talk is going to compute this CX psi. At least give you the formulation how to compute this one. First of all, I have to introduce the single parabolic subgroup. So we have X, then we can consider all the elements in SPW which take X to X. Okay, it will not stabilize every vector in X, but it takes a subspace X to X. So this PX has a Levy decomposition, so that its Levy part called MX is just isomorphic to GLX, and its unipotent part NX is actually isomorphic to symmetric matrices on X, or symmetric bilinear forms on X. So you have this kind of short exact sequence showing that PX has this kind of structure. The point is that the splitting S. Okay, so this SR is just by sending G to GRG. R is this giant integration. Okay. So it turns out when restrict on PX, this is a group homomorphism. Okay. And it has also satisfies some kind of compatibility condition, like it with respect to the block decomposition. So I will skip it. And so there's also another case when it's restricted to a group homomorphism, is that if you consider WS like this, so you choose a symplectic basis. After that, you have the WS like this. This is basically the representative of inside the representative of the Weil group or Weil group of a symplectic group. But this WS will represent the collection of WS will represent classify the double coset decomposition of G by the single parabolic. Okay, so this, if you take WS, then you consider the group generated by WS. Unfortunately, it is not equal to the collection of all WS. This is will be an extension, plus minus 1 to the power n extension of WS, something like this. As you know that in general, this Weil group cannot be split in send in back to the original. Okay, so anyway, restrict on this W, you will also have a group homomorphism. And the point is that each of this WS is certain partial Fourier transform. Right. So this is a key point, I think. So you see that Weil representation is highly connected to this Fourier transform. Okay, to evaluate this CS as a cocycle, we have to introduce another very heady notion called the Weil index. Basically, the setting is like this. If you have a symmetric bilinear form, it is actually related to a homomorphism from X to X star, such that B. So this bilinear form beta XY is equal to BX and BX paired with Y. So this is linear algebra. And this symmetric bilinear form will associate to a quadratic form by send X to beta XX. And the quadratic form and the bilinear form are associated by this formula. Okay, so what is a character of second degree? So a character of second degree associated to the symmetric bilinear form is just this form. Okay, it's an evaluation of its value of the quadratic form by this non-trivial additive character set. Okay, it's not a character of X. It's a character of second degree because it's a quadratic form here. This is the notion defined by Weil. Okay, so from this character of second degree, you can define a unitary operator by this integration formula. And as you know that Weil representation is related to Fourier transform, so you can compare the action of the character of second degree and take the Fourier transform and the Fourier transform of any arbitrary functions phi with multiplication of this guy. Okay, it's pretty technical. The message is that the two sides are essentially the same, but up to a scalar. This scalar is called gamma f beta. Okay. So we will call this non-trivial element in C cross be the Weil index. Okay, so the message is that Weil index is for each quadratic form or each symmetric bilinear form, you will have a Weil index. And it turns out for quadratic space, you have a quantity group of quadratic space. And you mod out the V. So there is a relation that V and W are the same if V is equal to, so there exists a hyperbolic collection of hyperbolic space such that V plus hyperbolic space equal to W plus certain copy of hyperbolic space. Then this will form a additive group called the Witt group on the for quadratic space. And it turns out this Weil index is a group homomorphism, descends to a group homomorphism on the Witt group. And as a corollary is that because this is a group homomorphism and the Witt group for local non-Archimedean field is actually a group of order 8. So therefore, this number is in mu 8. a group homomorphism from degree, a group of order 8 to C1 is actually, sorry. So actually, in fact, this is, this number is not only a complex, non-zero complex number, also has modulus 1. So it's on the unit circle. So therefore, you know, it is actually mu8. Right, there's a very interesting calculation of the Weil index is that you consider the case that F is a local field and you take E to be the quadratic quaternion algebra over F. There's a unique one up to there's a unique one up to isomorphism of quaternion algebra over F for a local field F. Local non-Archimedean field. Right. For R, there also has a 1. So, okay, so but let's focus on the PAD case. So, and then this ND is a norm on on D. This is a quadratic form. Then this quadratic form, the Weil index of this quadratic form is equal to -1. So, how do you prove it? You just use brute force computation. Okay, so there's another notion called the relative or normalized Weil index. So because this Weil index is actually depends on psi, so on the other hand, you can have a psi A, so which means that for any F to F, you set X to psi A, sorry, it should be psi A X. Okay, so all the non-trivial additive character is given by psi A for A varying over all non-zero element in F. Okay, so then you can compare the discrepancy between gamma psi A and the gamma A. So this is called a relative Weil index. Okay, so it satisfies certain properties, like, you know, it's actually descends to F cross over F cross square, because gamma A B square is equal to gamma A. And it's also multiplicative up to the Hilbert symbol. So this number, so because it's an ingression and it's related to additive character, so it's not surprising that it's related to epsilon factor. So I think this Weil index, relative Weil, normalized Weil index is actually the epsilon factor of take for the character psi, if we take E to be the extension of F by the square root of A. And this chi E is a quadratic character related to the field extension. And this delta E is the discriminant of E over F. And this X over delta E over F is the Lagrange symbol. So if you are not knowing anything about this symbol, don't worry. So when I was PhD, I know nothing about this. So anyway, I think the important thing is that you receive the message that this gamma A psi is actually give you some arithmetic information of the field extension, quadratic field extension. So the similar situation happens for the finite field case. So if your F is a finite field, then this gamma A psi is nothing but the Lagrange symbol, which this one is 1 if A is a square and is -1 if A is not a square in the finite field. Okay, so this Weil index actually has a multiplicative property. So as we know that all the quadratic space, for any quadratic space, you can find a basis such that on the basis, this quadratic form is given by a diagonal quadratic form with diagonal number A1 to AN. Okay. Then you can define the determinant of the quadratic form. This is nothing but the multiplication of the diagonal, but this is only well defined up to square. And you also can define Hessian invariant of the quadratic form. This is given by the product of Hilbert symbols of Aij, where Ai is less than Aj. Okay, it is known that the quadratic spaces are classified by determinant, Hessian invariant, and the dimension of the quadratic space for the p-adic case. P-adic case. Okay. Then you have this kind of multiplicative formula for the usual weight index and the relative weight index. So you see that the difference between psi and the gamma psi to the power n is totally controlled by the determinant and the Hessian invariant. Okay, so this is one part of the story. Another part is that, hopefully I can finish it today, is that we still want to define something called a Lagrange invariant. So recall that a Lagrange is a maximal isotropic subspace in W. So we consider the collection of all Lagranges. So for example, in the polarization, you have W equal to X plus Y, and the X and the Y are both Lagranges. Okay, so this collection of Lagranges is a symmetric space. It is a flavor, generalized flavor. So this is nothing but G mod P actually. Okay. So all the Lagrangians on the G action form a single orbit, and the stabilizer of a single Lagrangian is a single parabolic. So therefore, it is G mod P. Okay, so now let's consider triple product of the space of Lagrangians. Okay, so we want to, you have this triple product and the GX on this triple products. It turns out it has finite orbits. Right, it has finite orbit in this case. But we want to define a map from this to the set of quadratic space over F up to isometry. So its image is called a Lagrange invariant for this triple X1, X2, X3. Okay, so it turns out also this orbit on this triple product is classified by the dimension of intersection of this 3 space and the intersection of arbitrary 2 space and the Lagrange invariant, because each of these coordinates are finite set. Right, so therefore you see that SPW orbit on the triple product is actually a finite set. Okay, so how to define a Lagrange invariant? So the generic case is that arbitrary 2 subspace, Lagrange subspace in the 3 Lagrange subspace X1, X2, X1, X2, X3, the intersection is 0. In this case, W can be written as X1 plus X2. Okay, in this case, you have this decomposition. And the third space can be translated under a unipotent element in the single parabolic under this decomposition, so that there exists a unique U, have the form 1B01, such that the U x2 is equal to x3. And we just define the Lagrange invariant to be the quadratic form on x2. Okay, so the non-generic case is that you have some intersections of this quadratic, the Lagrange spaces are non-trivial. In this case, you reduce to the generic case. So you define M to be the summation of x1 instead x2, x2 is plus x2 instead x3 plus x1 instead x3. And you define M Wn to be M perpendicular divided by N. And then you look at the image of these Lagrangian spaces inside this Wn, more or less. So the Levy invariant of x1, x2, x3 is defined by this way. So it's just the x1m, x2m, x3m, the Levy invariant of these three spaces. And a simple property like if you commute the space, you will have a sign of the sigma. Okay. But the main theorem is that the cocycle is actually given by the Weil index of the Levy invariant of x, g1 inverse x, and g2x. So this is the point. So after almost 70 pages of calculation, they reach this formula. Okay, as a corollary is that, for example, you have Levy invariant of also have like the cocycle has this kind of formula, and also G inverse, the cocycle for evaluate that G inverse is 1. Okay, so as we certainly all heard about, the Metaplectic group is a double covering. So, but in this case, we know the cycle is actually taking mu8. So it's an eighth covering. So how to bridge from the eighth covering to the double covering? So you need to like have a cycle which co-homologous to this cycle, which take value in mu2. Okay. So this is the work of Rao. Yeah. So I never be able to understand his paper. Okay, but luckily, so Gan-Kudla-Takada has carefully do everything again, and in a modern way, in a consistent way. Okay, so what you do is first you define a Rao function. So this is just a determinant of P1, P2 restrict on X. So where P1, P2 is appear in the generalized Buchau decomposition with respect to the single parabolic. Okay, this WS is the specific splitting I showed before. So it's this, right? Is this element. Okay, so every element in G can be uniquely written as P1 WS P2 for certain S. S is a subset from 1 to N. Okay. So then you define this function beta psi x to be this one. Okay. So magically, if you define a cocycle Cx by this formula, then by definition, this Cx is actually a cohomologous to the Levy cocycle. But the point is that you can calculate this one. So that Cx equal to the Hilbert symbol of the Levy of the Rao function, value of Rao function for G1 and G2 times. Okay, so anyway, this is a very big formula. The point is that each term are just plus minus 1. So therefore, the multiplication of these terms is just the element in mu2. Okay, so therefore, so there's some additional formulas, but as a consequence is that you use this cocycle, you can define a Metaplectic covering, define a double covering of MPW, SPW. so therefore it will afford the Weil representation. Okay, so we will discuss more details next time. Thanks.